So the story all started long time ago when Einstein was only 16 years of old. And he wondered about the nature of the world around him. And he asked a lot of questions. One of these questions is on Maxwell's equations. So it all started out with Einstein thinking of Maxwell's equations and what gives rise to the Maxwell's equations. So he basically asked himself, what would I see if I was writing a light beam? And basically what the normal answer would be when you think about that question is everything would look frozen. Basically, when you're writing a light beam, you would be moving at the same speed as the speed of light. So then everything would look frozen to you, including light itself. So the way that Maxwell described light and the electromagnetic force are portrayed in these four equations. And these equations basically tell us everything we need to know about the electromagnetic force, how light interacts with matter, and how the electric field gives rise to the magnetic field and vice versa. So basically, light, according to Maxwell, is portrayed as this. This is a simple diagram of how light basically works. And what we see here is we have one part is electric field and the other part is a magnetic field. So what was very successful about the Maxwell's equations is that Maxwell was able to unite between the electric field and the magnetic field in light. Basically, he described light as a combination of both fields together. So when Einstein came along when he was 16 and asked the question, what would I see if I was writing a light beam? He would be basically seeing light frozen as well, including everything else. But that does not make sense because according to Maxwell, when he input the data into the equations and he calculated the speed of light, he reached a speed of 300,000 kilometers per second. So basically, if Einstein was writing the light beam, then that would mean there is no speed of light, that light is frozen, and that is impossible. Because light, as we will see shortly after, is a constant of nature and it should always have a constant speed. We will see how that question gave rise to Einstein's special theory of relativity later on when he was 26, thinking of nature. But this is the beginning of Einstein's thinking on the special theory. And that was his line of thinking, is basically he went from Maxwell's equations and he was thinking about light in that sense, and then he combined it later with motion as Newton used to see it, and we will see how that will play out. So these are basically the principles of special relativity. They are what makes the special theory of relativity. These are the fundamentals that Einstein laid out in his 1905 paper on the electrodynamics of moving bodies. I will attach the link of that paper below the video. You can check it out, give it a read. It gets complicated. The longer you read, the further you go, but it starts out very easy. You will see that he talks about Maxwell a lot in this paper. So basically, these are the principles of special relativity. The first one is the laws of physics are identical in all inertial frames of reference. And what that means is an inertial frame of reference is anything you can relate to your physics, basically, that you have a starting point. For example, what's your motion relative to me? Then I am a frame of reference that you can kind of reference to. A good example on this that illustrates this principle is imagine you're in a train and you have a ball and you decide to throw that ball upwards. It will come right back to your hand as the train is moving. That's basically because the laws of physics act the same in a moving frame as in a stationary frame if it was moving in a constant speed. And that's basically what it means. But if it was an observer outside the train observing you throwing the ball as the train is moving, then the path of the ball would be curved instead of straight. And that's basically just depending on where you are, if you were moving or stationary. And that kind of what gives relativity the name, relative, basically. On the second hand, we have the speed of light as a constant in vacuum. So what is happening here is basically this principle gives rise to this principle. Since the speed of light is a law, then it should be identical in all frames of reference, hence it is a constant. So for example, if you were to throw the ball this way as the train is moving this way, then you would normally you add the velocities of both objects together and then you would get the total velocity of the ball. So it would be v ball, the velocity of the ball, plus the velocity of the train would give you the total velocity. But when it comes to the speed of light, this is not how things work out. Speed of light is a little bit different. That's what makes the theory special. Basically, if you were to do that, if you were to shine a light beam as the train is moving this way, then this relationship wouldn't work out because you cannot add the speed of the train to the speed of light. You would only get a constant. The speed of light is the same anywhere and everywhere you go, no matter what you ride, no matter where you are. So this is what makes the special theory of relativity the theory. This special component is that the speed of light is a constant, and we will shortly see how that comes into play from Newtonian equations that I will write down for you here. So now I will show you how we will go from Newtonian mechanics, kind of simple equations, it will stay simple, and how we will go from here to Einstein's realization of how it's not working out and how he realized that he had to tweak a few things that were very small, as we will see, but then it gave a radical change to the field of physics and changed the way we look at everything pretty much. So basically, let's start out with a moving object, very simple, and this is the equation of the moving object. This equation describes the position, and it comes from this expression. We've all seen this in high school. Velocity is position over time. So we kind of manipulate that. We get this expression. And basically, if we kind of want to zero the equation to kind of make it more descriptive, I would make it like this. Zero it, x minus vt. Now, it's easy for me to visualize the movement of the object. And how do we do that? We do that by these diagrams. It's called space-time diagrams, I think. And trust me, you've probably seen a lot of diagrams, and you're probably like, oh, I don't like them. I didn't like them too. When I first started university, I didn't see any use to diagrams, but then I realized how important they are in giving us a lot of information about things. So many things can be calculated from diagrams, because it gives you a relationship between two separate things, and then that relationship can tell you a lot of information. So basically, let's graph the movement of the object or the motion of the object. So normally, this equation would look something like this. And this is basically the defining expression. And let's imagine there is another object. Let's call it x prime, and it starts in the origin, and that's basically the object's reference frame. It starts from here. This is how we're seeing things. So according to Newton, if Newton was still here, he would heavily disagree with Einstein, and we will see why, because he will say that my time is equal to your time. That's a defining feature of Newtonian mechanics. What that basically meant is that time is absolute. That time, a clock clicking here in the Milky Way galaxy would have the same time as a clock clicking in the Andromeda galaxy. Time is some sort of universal parameter that does not change according to Newton. But that's entirely different in the special theory of relativity, of course. So basically, starting out from there, we will get an expression that describes the position of this reference frame in terms of those parameters. So how would it look like? It would look like something like this. X prime equals x minus vt. Now this is a new equation that would describe the motion of another object in terms of the parameter of the things we have here, the parameters that what we know. So basically this shows for an object here how far this object from me with the things that I know. And this is basically the simple Newtonian mechanics, and we will see how that changes to Einstein in a second. So we can also write the equations that we wrote before like this, plus vt prime equals x. So basically I did some manipulations here. Since I already written t equals t prime, I can just sub this in here and then sub x prime in here, and then I get this expression, which is basically a different frame. I'm kind of going back and forth here. So in my frame, I have light is described as this. We have this equation. This is for a normal moving object, but for light, it's this. So in my frame, how would this look like? Now imagine, this is the key here. Imagine it's purely Newtonian, right? We don't have the second principle of special relativity. Light is not a constant here. It's just a normal speed. So if we have this, right? If we have this idea and we kind of implement it in Newtonian mechanics, look what's going to happen. So how would this look like in a moving object? So I'm going to sub this into these equations and we'll see. So I have x prime plus vt prime equals, since x here is equal to this, I'm going to sub this in here, and t is of course t prime from this as it changes. And then I keep kind of simplifying the expression. So I get x prime equals ct prime minus vt prime. I group the t primes, and I get c minus v x prime. Now this is the key equation here. What does this tell me? The term c minus v tells me that for a moving object, it would have the speed of light has to be less than c, because it's being subtracted by v. And that's very wrong according to special theory of relativity and according to Maxwell's equations. So here where the time is not absolute, gets destroyed, and Newtonian mechanics does not make sense anymore, is if I assume the same time everywhere for every observer, I would get this result that tells me speed of light has to be less and it shouldn't be a constant. But everything else in the equations, especially Maxwell's equations that are proven to be right at all times, says that the speed of light has to be a constant. So Einstein had to change something here, very fundamental, in order to get his theory right. So what did he change? He made time relative, and he did not equal the two. And when he made that, you would get two different times that would give you totally different expression, and it would maintain that the speed of light is a constant. And this is basically how Einstein reached to his realization that the speed of light is a constant and time is relative from Newtonian mechanics. And this is basically what I wanted to show you, just very simple math of how things came to be and what gave rise to what. And these are kind of the initial equations that Einstein wrote down. And then it gets more complicated as if you check out the Einstein paper, he gets deeper into differentiation and then talking more about Maxwell's equations, and then time dilation, and then length contraction, and the Lorentz factor, and all of these come into the picture of the special theory of relativity and its wonderful results. It's a very, very interesting theory. I love the theory. It's very cool. And when I got to learn this, it was some sort of like enlightenment, because I was like, oh wow, like this is how it works. This is what made Einstein think that time is relative and it's not absolute. And by the way, the idea of changing time from absolute to relative was something crazy that shocked the entire physics community back then, because they believed that time is absolute for 4 centuries since Newton. But basically this is all of it. In the next video, I will explain to you, starting from these equations, time dilation and length contraction, and how the mathematics describes how things look like and how time clicks from the equations of the special theory of relativity.